This is part 2 of the Chapter 6 lecture notes, and we're starting with slide number, it's either 45 or 46, I can't remember, but I think it's 46. So the components of bone are separated into the organic components, which includes the bone cells for sure, all the different bone cells. And then the osteoid is basically the part of the bone matrix that is organic. So it's secreted by the osteoblast. So it's going to consist of the ground substance and the collagen fibers. So the osteoid makes up 1/3 of the bone matrix. Okay, so it's going to consist of ground substance and primarily collagen. So I always teach it that 1/3 of bone matrix is collagen fibers. But the inorganic component of bone matrix is hydroxyapatite. Hydroxyapatite is basically calcium phosphate. And so it is inorganic. It doesn't have carbon and hydrogen together. In fact, I don't even think it has any carbon in the chemical formula. But it makes up the other 2/3 of the bone mass. So, or almost 2/3 of bone mass. So bone matrix is the organic component is called the osteoid, and it's primarily collagen. And that's 1/3 of the bone. And then hydroxyapatite is primarily calcium phosphate crystals. And that's going to be the hard cement-like substance that surrounds the collagen fibers. And it gives the bone its hardness. Anyway, it makes up like almost 2/3 of bone mass. The term ossification, or sometimes we use osteogenesis, is the word for bone tissue formation. And then it gives you a little bit of the formation of the skeleton begins at during month 2 of the development of the embryo and the fetus, and then postnatal bone growth occurs until early adulthood. And also our bones are constantly remodeling and repairing throughout our life. So there's really 2 types of bone formation in the fetus. There is the formation of long bones occurs through endochondral ossification, and that is when the bones the long bones, like the bones of the upper limb and the lower limb, they're going to start out as a hyaline cartilage model. And then over time, bone tissue will replace the hyaline cartilage. So that's why the word endochondral, because chondra means cartilage. So endochondral ossification is when bones are formed, when the bones of the arms and legs and fingers and toes are formed, and that's through endochondral ossification. But then there are some bones, like the skull bones, that develop through intramembranous ossification. And that is, those bones form within a membrane, and they don't start out with a cartilage model. Okay, endochondral ossification, here are the steps, and you do need to be familiar with the steps. So let's look at the steps in the illustration first. So the first thing that happens, you can see this is just a typical long bone, and this is week 9 of development. This is when the fetus is 9 weeks old and still in the mother's womb or uterus developing. So this is early on, because you got 40 weeks, so this is just within the first 10 weeks of development. So this long bone starts out as a cartilage model, a hyaline cartilage model, and a bone collar begins to form on the edges where the diaphysis is going to be. and then a primary ossification center forms in the diaphysis region. Okay, so primary ossification center means that the cells that, the cartilage cells that are here in this ossification center are going to first of all hypertrophy. That means they're going to get larger. They're going to enlarge, then they're going to die, and they're going to be replaced with bone cells. Okay, osteoblast. And then in step 2, it says the cartilage calcifies in the center of the diaphysis, and then it begins to develop cavities. So first you have bone tissue that forms in the center of the diaphysis, and then you start, the medullary cavity begins to form. So osteoblasts are putting the bone tissue, they are secreting the bone tissue, and then osteoclasts are removing bone tissue to form that cavity. And you can see in step 3, you have, it says the periosteal bud. That's a blood vessel of, it says the periosteal bud invades the internal cavities and spongy bone forms. So we still got bone formation in the diaphysis, but we also have blood vessels entering. I hesitated because I never heard that term periosteal bud before, but it's just a bud is a growth. So it's like a growth in the periosteum, I guess you would say. In step 4, you're starting to see bone tissue formation in the epiphyses of the long bone, and blood vessels are invading the diaphysis and the epiphysis as well. We call the ossification centers in the epiphyses, we call those secondary ossification centers. And then you're going to see the epiphyseal plate is the cartilage that remains between the epiphysis and the diaphysis, and that's where growth is going to continue as the baby grows, longer and wider. This epiphyseal plate, this cartilage that forms the epiphyseal plate, will remain until adulthood. And then articular cartilage is hyaline cartilage that is left at the ends of the long bone. And it's called articular cartilage because that is where the bone connects with another bone at a joint. So that's the 5 steps. We'll go back and make sure you have your notes. So endochondral ossification forms all bones inferior to the base of the skull except for the clavicles or the collarbones. So, and basically, most of those bones are long bones, but it's going to be everything besides the skull bones and the clavicles or collarbones. So this begins in month 2 of development, toward the end of month 2, and it uses, it basically replaces a hyaline cartilage model with bone tissue. And here are your steps. In step 1, you have a bone collar forming around the diaphysis of the cartilage model, and you also have primary ossification center forming in the diaphysis. I'm not going to highlight these. You just really have to go through them. I like the notes that go along with the illustrations, but I would say for step 1, you need to know that a bone collar forms in the diaphysis, and also I would add a primary ossification center forms in the diaphysis. In step 2, the cartilage in the diaphysis begins to calcify, and that means the cartilage is replaced with bone tissue. But also, and that is by the action of osteoblast. The calcification or bone tissue formation is by the osteoblast. But then osteoclasts come in and start forming the cavity by breaking down the bone tissue where the medullary cavity is going to be. So you have calcification and you have breakdown of bone tissue to form the cavity. All right, in step 3, you have blood vessels that are invading the diaphysis. In step 4, you have the medullary cavity forming completely, and that forms through the action of osteoclast. And then you have secondary ossification centers, and those appear in the epiphyses. And then step 5, the only cartilage that remains is the cartilage in the epiphyseal plates and the articular cartilage, which is at the ends of the bone. And all of this cartilage that remains is hyaline cartilage. Okay? So that is endochondral ossification. Sorry, let me go back. Then we have intramembranous ossification, and you don't need to know the steps. You just need to know for this, you need to know that intramembranous ossification is the type of bone growth that occurs in the skull bones. So it forms specifically the frontal bones of the skull, or the frontal bone is just one, the parietal bones, the occipital bone, there are 2 parietal bones, and there are 2 temporal bones, and the clavicle bones, which are the collarbones. Okay, the collarbone bones. Anyway, that is just kind of shows you, I'll show you the pictures, but it's basically bone forms within a membrane. So it's intramembranous ossification. And then you have bones that grow longer and thicker. They grow lengthwise or grow longer. That growth is called interstitial growth. And that is by the growth at the epiphyseal plate. And then appositional growth is the growth in thickness. And then bone tissue stops growing during adolescence. Some facial bones continue to grow slowly throughout adulthood, throughout life. And this explicit is going to show you how the bone tissue grows longer. And I didn't ask any questions about these zones. So you don't, for the epiphyseal plate, I just want you to have an understanding of the basics of how it works. So during at the area that is labeled hypertrophic or hypertrophic zone, that is the area where the cartilage cells, the chondrocytes within the epiphyseal plate, which remember the epiphyseal plate is composed of hyaline cartilage. So those cells enlarge, that's hypertrophy, and then they're going to die, okay? And then the cartilage cells in the proliferation zone undergo mitosis. So basically, as the bone tissue replaces the cartilage cells that are there, new cartilage cells form ahead of that bone tissue so that you can continue to have an epiphyseal plate. So the only thing really that happens, I'm trying to find like a place that, yeah, here we go. This is a good picture. So we had, before the bone grew longer, there was an epiphyseal plate here. So the cartilage in this plate is replaced with bone tissue, and then new cartilage grows ahead and then also below. New cartilage tissue is going to form so that you still have an epiphyseal plate. So this cartilage tissue that you see in the picture on the right is actually new cartilage. The old cartilage has been replaced with spongy bone. Okay, so that is how bone grows in length. And also here, the cavity will get longer too. So you see there's bone tissue at this point that is right above that medullary cavity. Well, that bone tissue will be broken down by osteoclasts so that the cavity gets longer. So there's no bone tissue where it used to be. So hopefully you can understand that. So as the bone grows in length, the epiphyseal plate kind of moves up and reforms above the new bone tissue, and the cavity gets longer because osteoclasts remove the bone tissue, so the cavity can also grow in length. All right, regulation of bone growth by hormones. The most important hormone that regulates bone growth is growth hormone. And it is the most important hormone in stimulating epiphyseal plate activity. Then thyroid hormone modulates the activity of growth hormone. So it works along with growth hormone, ensuring proper bone proportions. The sex hormones, testosterone in males and estrogens in females, at puberty, they have a surge, males and females have a surge in testosterone or estrogen, and that will lead to growth spurts in adolescence. And growth will end when testosterone and estrogen induce the closure of the epiphyseal plate and the formation of an epiphyseal line where that plate used to be. Now, anytime that there are abnormal amounts of any of these hormones, excess hormone or deficits, in other words, not enough of these hormones, any of these hormones that you don't have in the right amounts at the right times can cause abnormal skeletal growth. All right, so I'm going to stop here. Well, no, I'm not, because bone remodeling is short. So I'll do bone remodeling and then stop. Our bones continue to, it's kind of like our skin. We shed the top layer of skin about every 3 weeks, and it's replaced with new skin cells. So bone remodeling is kind of like that. It's just slower. Spongy bone is replaced every 3 to 4 years, and compact bone is replaced every 10 years. So bone remodeling happens throughout our lives, where we are constantly losing bone tissue and replacing it. Bone remodeling consists of depositing new bone matrix with the action of osteoblast, and then bone resorption, which is really, it's called resorption because bone tissue is breaking down, osteoclasts are breaking down bone tissue, but it's the calcium and minerals are being reabsorbed back into the blood. So it's helping to increase your blood calcium levels. And bone remodeling occurs at the surfaces of the periosteum, which remember is the surrounds the entire bone on the outside, and then the endosteum lines the inside of the bone in the medullary cavity. Okay. Bone resorption is the function of osteoclast. So they basically release these enzymes that break down bone matrix. They secrete lysosomal enzymes, and they also secrete protons or hydrogen ions. And these together, that basically functions similar to how protein breakdown occurs in the stomach, because you have hydrogen ions released, which increases the stomach acid level, and it lowers the pH. And then enzymes are released that break down the proteins that we eat. So this is very similar to what happens in the stomach to our food that is, to the food that we eat that is protein anyway. So basically, osteoclasts secrete enzymes and they secrete hydrogen ions, which is going to create like an acidic environment. So it will lower the pH and digest the bone matrix. And it tells you the reason for the low pH, for the acidity, is that is necessary to convert calcium salts into soluble forms. So you can't break down those calcium phosphate salts without an acidic environment. So osteoclasts also are phagocytes. They phagocytize basically old matrix. Demineralized matrix is really like the osteoid, the collagen fibers, and dead osteocytes. So they also act as phagocytes, and The activation of osteoclast involves the hormone PTH, or parathyroid hormone, and immune T cell proteins, but we'll just worry about PTH. Okay, so parathyroid hormone will activate osteoclast. The osteoclast will break down the bone matrix, and then the excess calcium will be reabsorbed into our blood, and it will raise our blood calcium levels. So parathyroid hormone is actually released by the parathyroid glands when our blood calcium levels are low, and it will activate osteoclast, and as they break down bone matrix, calcium will be released into the blood. Okay, we're going to have to stop here. This is 20 minutes. So we are going to stop at slide 73, and we will begin at slide 74 in the next recording.